is continuity on an open interval. Okay. What we have is, first of all, we've got to talk about, make sure everyone understands what this notation stands for. Right here. That's not a point, an open interval. Another way of expressing the open interval would be to say that A is less than the input is less than B. And I know it's less than and not less than equal to because they're parentheses. If they were brackets, so if we had a bracket on one side, such as this, it would be A less than or equal to X less than B. So just a little note about the notation. I don't use the open interval that much, although it is a very convenient way of writing it. But take a look at that and make sure that you understand what we're talking about here. Okay, so a function is continuous on the interval if it's continuous at each point in the interval. Now, I have to be honest, some of these I look at and go, well, yeah. If it's continuous everywhere in that interval, then we have that it's continuous on the open interval. So, I don't spend a whole lot of time discussing this. It's just one of those statements, though, that as we do proofs in mathematics, we need to have statements like this to be able to go back and, your proofs in geometry, and you have to go back and make the statement. So that's just what that's for. Removable discontinuities. A discontinuity can be removed if the function can be made continuous appropriately by appropriately redefining f of c. Now, we have done some of that work in our limit section. If we had, let's say, f of x is, well, no, I'm not going to do that. I'm not going to do that. I'll save the examples for that because I want to make sure that we don't think of it as just redefining the function, because when we redefine the function, we still could have that discontinuity. So let's just look at some examples, and this will come up again. Okay, here we go. Hope you're getting used to this notation, x plus delta x. Delta x stands for what? Change of, okay, the difference between inputs. So delta x is not an input, it's the value that represents the difference between the inputs. Okay, find the limit if it exists. Well, the first criteria is, well, excuse me a minute, let me get my thoughts on this problem. We're finding the limit. We're not really talking about continuity, so we're not going to talk about those limits just yet, or those criteria just yet. But let's just talk about this, because part of this discussion is on one-sided. If we're looking at one-sided limits, what does this represent? I'm going to highlight it here so we have it. What does this represent? From the greater than 0 side. So that means that as we approach, as the differences are positive differences, so you could have a negative difference if you approached, if you took two x's and moved them in a way that when you subtract one from the other, you get a negative quantity. So we're just going to be working on that. Actually, on this problem, if we're going to work this one, and I want the limit, I'm going to work it as if it just says 0. I would work it exactly the same way. Now, when I get my answer, then is when I might need to look at this criteria and say, well, really, I have to be careful now with my answer because I cannot have answers that are less than 0. So I'm going to work this problem as if it's just equal to 0. But I will put this up here, but I'm going to work it as if it's just equal to. Okay, or just approaching 0. So let's see, we have x squared. You should be able to, I would expect you to be able to multiply out a binomial squared. By the way, I kind of assume, and I guess it's a wrong assumption, that by this stage of your mathematical career, you no longer use the x for multiplication. But I find some students still in Calc 1 using the x for multiplication. Do not use an x to indicate multiplication, because we now know x to be a variable, not a symbol in that respect. So use the multiplication point, or just put it in parentheses. Okay, so plus x plus delta x. And then the other thing I just have to remind you about, I shouldn't have to, but I know that we all sometimes have some of those mental moments. When we have subtracting a binomial, what do you have to be careful about? Yeah, carrying through the subtraction sign. And I know every one of you is going to make that mistake. If not on a quiz, you're going to make it on your homework. So just be real careful. Now the way to make sure you don't make those little simple algebra 1 mistakes is to make sure that you put parentheses around quantities. And I find students on quizzes and tests not doing that. So be sure that you enclose in parentheses when necessary. This is not this was given to us with proper grouping symbols. Okay, the other thing I want to remind you about, may I dismiss writing this? No, absolutely no. When can I dismiss writing it? And by solving it, I will have done what? Use direct substitution. Okay, I must carry it on until I use that direct substitution. So please, this is the one place where students miss points so much on the quiz and the test when we have things like this in the limit, because you assume you don't need to write it. And again, my example is, if I gave you the square root of, let's say, x squared minus 5, is it correct to just write it as x squared minus 5? No. It changes the whole problem. Same thing here. It changes the whole problem if you don't have that. So be real careful about that. Okay, let's check our time here. Oh, good. Okay, so as we look at this expansion of this, and by the way, when you do this on the Inspire, you can't put delta x in. What will you put in in the Inspire instead? I wouldn't put a y. Too many of you think y means an output value. You can't put a y in here. You could, but I just would not suggest it. Often you find other books put an H. H stands for the difference. Okay? Anything except, don't try to put delta x because it doesn't recognize it as a variable. So put an H or a W or something in there. Okay, so as I go through this and I look now at my work, is there anything that can simplify up here? And so we go through and we mark out everything that can cancel. And at this point, every term that's left, I'm going to circle these right now, every term that's left in here has something in common. What is it? And that's important. Why? Why do we need to be able to do that? And I couldn't otherwise. Absolutely. Okay. So there's a purpose for needing to be able to cancel all of the terms that do not have a delta x in them. The delta x is the reason why we cannot use direct substitution. We went over this before, but it always bears repeating, it seems. Okay, so now we've got this. Okay, and now at this stage, can I use direct substitution?
Yes.
Absolutely. And I would have 2 times 0, right?
Yeah.
Why not? Be sure you only insert the delta x where we have a delta x. The 0 where we have a delta x. Okay, so we end up with 2x plus 1. Okay, I worked this, I think we did the very same problem in another section, probably section 2.4. Very same problem. The only difference is this has a little plus up here, which means that if I'm looking at approaching this or drawing this, I can only approach from those values greater than 0. And that means the change in the difference between the inputs is a positive quantity. Okay. There we go. So that's just a little example of a one-sided limit, but again, approach it just like you would any other. Now this is a completely different animal here. Okay, this is different. You know, I've told you I have calculus all day long. I have 2 sections of this Math 50, and I have a section of Business Calc. And I've told you that Business Calc and Calc 1 are identical. Same author, different textbooks, same author. And so the work that we do, in fact, I use some of the same examples for both classes, so I can't remember if I've told you this or not. Okay, I don't think I have. I think we got into this with that class on Tuesday, so if I'm going to repeat myself, maybe we just need to have it be repeated, but here we go. This is a function. Now the whole thing is one function. But we have a name for this type of function. Have we gone over it? Do you know what it is? Okay, have we gone over this? Okay, you just know it. Good. It's a piecewise defined function. Now, you've been working with some of these in your homework, so this should not be your first introduction to this. In fact, this class is not your first introduction to it. The name of that function tells you exactly what it is. It is a function that is defined in pieces. And we happen to have 2 pieces. Now, when we talk about continuity and we talk about these functions, we know that certain functions are continuous everywhere. I don't know that we've had that statement. It may be coming up later in our notes as a theorem. But let me just tell you this now. Polynomial functions are continuous everywhere. So if it's a polynomial function, it's continuous. We don't even have to worry about the 3 conditions that we were talking about. So if you look at this one piece here, this is a polynomial function. We recognize that graph as being a horizontal line. We know it's continuous everywhere. Cosecant. Okay, now that could give us some trouble, right? Do you know what the cosecant graph looks like? Yeah, it's a series of, and I may be drawing this wrong, we can go back and look. It's a series of things like this. It may be, I may need to shift that over a little bit, but it's graphs like that. So obviously we have some discontinuities. Okay, so we're going to have to be real careful about that one because we know that we might have some discontinuities in there. Okay, now the problem is that we're going to evaluate these 2 because, you know, if we have the cosecant graph that looks like this, is the cosecant function continuous anywhere? Oh, careful. Is it continuous anywhere? How about in here? It's continuous in there. Okay. And it's continuous in here and so forth. So it is continuous some places. Now I said anywhere, not everywhere. Okay, that may have been what you were focusing in on. And so it is continuous at some points. We need to look at what happens when we have this break in here. Okay, so we want the cosecant function, and we're going to evaluate it for absolute value x minus 3 less than or equal to 2. How many of you love to do absolute value problems like this? Yeah, that's what I thought. Okay, we're going to have to go through and we're going to have to rewrite this. Now, if you remember, when you rewrite something like this, you're actually rewriting it as a compound inequality. So we're going to take care of that and the same thing down here. So I'm going to stop this